Hi there and welcome to another Entagma tutorial. Today I want to talk about the bullet solver, and specifically about scaling bullet objects while the simulation is running. This effect is very nice and comes in handy for motion graphics, but you can use it for visual effects too. Before we dive into Houdini and build the effect, we have to talk a little bit about packed primitives, because the bullet solver usually works with packed primitives because it's more efficient than standard RBD objects. And we will eventually modify the intrinsic transform of the packed primitives to make this effect happen. So let's dive into Houdini and build ourselves a bullet simulation from scratch. To start, let's put down a GeoNode and dive inside, get rid of the file swap as usual, and let's put down a grid. I want to create an array of boxes, so let's create a box and a copy to points. And using this, I will copy the boxes over to all the points of the grid. I need more boxes, so let's up the subdivisions of the grid to say 50. And to compensate for this, let's go down with the uniform scale of the box to 0.15 maybe. Now we have a nice grid of boxes, with the boxes not interpenetrating. It looks a little bit boring. Let's vary the orientation. Normally you do this using the normal attribute, the N attribute, but I prefer the orient attribute because I usually work with WOPs to do something with the orient attribute, and it's more precise to do it this way. So this time let's use the orient attribute. I put down an attribute create, put it here beneath the grid, and let's create an orient attribute. Remember that orient is a quaternion, meaning it's a vector with 4 components, so the size has to be 4. And now we can use an attrib randomize to randomize the orient. Just put orient here instead of CD, and we have a nice random rotation on all of the boxes. Now before we put all this geometry into DOPs, let's first talk about packed primitives. Because if I put all of this here into a DOP.NET and try to simulate it with the bullet solver, what I get is just one big dynamic object. And this is not what I want. What I could do is split apart all these boxes and then try to create one RBD object for every box, but this would be overkill because I have really a lot of boxes here. Fortunately, side effects invented something to overcome this complicated situation, and that is packed primitives. As you probably know, primitives are the most basic building blocks of Houdini geometry. A primitive refers to a polygon or a NURBS patch or even a volume, or to a packed primitive. And a packed primitive is sort of a reference. It stores a transform and uses geometry stored somewhere else in memory. Let me quickly explain how this works. Let's have a look at this box here. One nice box. It consists of 8 points and 6 primitives. And the transform is defined by the containing object. So this is at the moment GO1. And here is the transformation matrix. If I have more geometry inside of this object, one transform is used for all of this geometry. But if I create a pack node, the easiest way to create a pack primitive, and then pack this box, I'm left with 1 point and 1 primitive. Where's all the geometry gone? Well, Houdini stored all this geometry away in memory. And the pack_swap just created 1 point to reference this geometry and to store the transform of the geometry. If I look into the geometry spreadsheet, all the geometry is gone and I'm left with 1 point, which is not translated at the moment. Where's the rotation, you ask? Well, the rotation is on the primitive. And it's stored here in the intrinsics. What are intrinsic attributes? Well, intrinsic attributes are standard primitive or point attributes, but they are set or calculated by Houdini and used internally normally. So in this case, we have this transform here, and this transform, if I expand this window a little bit, is just a 3x3 matrix. So it's just storing rotation and scaling. That means using the transformation here of the point and the 3x3 matrix stored in the intrinsic attributes, we have a full transformation matrix. We can generate a full 4x4 transformation matrix with homogeneous coordinates from this. And this is what Houdini does. And then it adds a pointer to the geometry that is stored somewhere. And that means if I duplicate this, I don't get the double geometry, but I just get 2 points. So if I put this here into the copy to points, what I now get is all of the cubes back. But now I'm left with 2,500 points. And that is because the grid happens to have 2,500 points. And all of these points, or all of these packed primitives, are referring to the same set of geometry. You already see that this is far more efficient than using individual geometries here, in this case. The good thing is I don't even have to use this pack node. I can get rid of it because it's already built into the copy SOP. I can just check pack and instance, and this gives me pack primitives. If I do this, 2,500 points, 2,500 primitives. And a quick look on the geometry spreadsheet shows me the points, 2,500, and the primitives, and the intrinsic transform of the primitives. So basically I have transformation matrices referring to geometry in memory. And this geometry is used by the bullet solver to build its collision geometry from. And then the transform is used to be simulated. Mantra can render packed primitives directly because Mantra just generates the geometry on render time. Because it knows where the geometry is stored, then it transforms the geometry and renders it. And the viewport in Houdini can very efficiently display the geometry using the same trick, using the same geometry over and over again and just transforming it by the transform stored on the packed primitive. So great, now that we have an array of packed primitives, we can go into DOPs and simulate this. First, let's clean up. Let's get rid of this unused pack node and now lay down a DOP network. Wire the geometry into the first input and dive inside. Now let's create a standard bullet setup. First we need a bullet solver, or in our case a rigid body solver, which encapsulates bullet, ODE and the standard RBD solver. But it's set to bullet by default. Here solver engine is bullet, connected up to the output, and then we need a RBD object. But instead of using the standard RBD object, we want to use the RBD packed object, because this one is specifically designed to work with packed primitives. Wire it up, and then let's specify the geometry that it should use. The geometry source here is pointing to a SOP at the moment. Let's just say first context geometry, and it happily imports all our packed primitives. At the moment nothing is happening because we don't have a force. Let's create a gravity force, wire it up, and press play. Bam! Everything explodes. That is because of our orient attribute. The orient attribute is copied over to the packed prims, as you can see here, one level up. And that is a problem because it distracts the bullet solver. So let's get rid of it. The easiest way to get rid of this attribute is to go to this to-point field here, where it states which attributes to copy over. Then put one of these little hats here inside and just specify orient. And that tells the copy to points not to copy the orient attribute. So now no orient attribute, and everything falls down. Eventually we want to make this stuff collide with the ground plane, and the ground plane normally sits on 0, 0, 0, so it's probably a good idea to transform all of this up a little bit in Y. Let's make this like so. And now we can create a ground plane. This ground plane needs a static solver, and we can merge it in using a merge node, like so. Connect the merge to the gravity, clean up a little bit, and now we have a standard simulation with the objects falling down, colliding with the ground, coming to rest eventually. So now for the scaling. But before we implement the geometry wrangle to do the dynamic scaling, we need some influence points, because I plan to have influence points here in space, and where these influence points are, the cubes should scale up. So go up one level and let's create some influence points. Just put down a scatter and scatter 4 points to the grid. Not 1,000, but just 4. And I want to have these points be in random locations in every frame. Let me turn on point number such that you see the points better. And I can achieve this by just putting $F here in global seed, so the seed will be different in every frame, and I have points on random locations. Always 4 points, but on random locations. And these will be used to generate the fall-off or the scaling. So wire this stuff into the DOPNet because we want to refer to it from the DOPNet and go inside again. Now let's create a geometry wrangle. And this will be used to do the scaling. So dynamically scale. And I want this to happen before the rigid solver does its work. So I have 3 inputs here on the rigid body solver. The first one is the object, the second one is pre-solve, and the last one is post-solve. So pre-solve sounds as if the stuff would be executed before the solve, so put it here. Now everything inside of this wrangle will be executed before the rigid body solver actually does its solving. Before we start typing code into this wrangle, we have to specify the inputs. I want to refer to these points I created earlier, so let's set input 2 to second context geometry, because this is the port on the DOPNet I wired the points into. And then we have to specify on input 1 myself, because I plan to reference my own geometry, and this handles the necessary geometry copying that is happening internally for me. Now that the wrangle is set up, press Alt-E and open the code editor. I make this a little bit smaller. And let's think about what we want to do for a second. We plan to get the transform of these boxes and then compare the position of the boxes to the position of the incoming points. And if the position of the boxes is inside of a given radius around these effector points, the stuff should just increase in scale. So let's do this. Don't forget to set this wrangle to primitives, because we want to run over the primitives. We want to get and set the transform, and this is an intrinsic attribute of the primitives. Okay, first let's just get the transform and set the transform, because this is special, as it is an intrinsic attribute. To get and set intrinsics, we have special dedicated functions. To get it, we use primintrinsic, and to set it, we use setPrimIntrinsic. So let's just create a variable of type matrix 3, because the transform is of type matrix 3, and use primintrinsic. Then geometry stream 0. The attribute we want to get is called transform. And we have to give it prim num to tell it which primitive to look for the transform. And then, of course, we want to specify a variable name. Let's call it myTransform, like so. Now we get the primitive intrinsic transform. And let's directly set it again. Set primintrinsic. The syntax is quite similar to normal set functions. First the geometry stream, then the name of the attribute, transform, then the primitive number, then the variable that holds the value to set, so myTransform, and last but not least, the little keyword set to tell the function what to do. Let's press apply and see if it works. Rewind, press play, and we have a little error here. Let's see what it states. We have a syntax error, and of course, as always, I missed a comma. That's a classic by now. No error. But of course nothing is happening because we just read the transform and set it again. Time to do something with this. Okay, we want to make the stuff scale in the proximity of the incoming effector points. So let's get these effector points, or for now just one of them. Create a new variable called vector tarpos and use a point function to look up geometry stream 1 in this case, because this is the effector points. The attribute we are looking for is p, and for now we are just looking for the very first point, which has the point index of 0. And now we want to define another variable called dist, which is a distance from our own position to this point's position. So distance, and then add p, which is the centroid of the primitive, so our own position. In the case of packed primitives, this just refers to the point position. And then tarpos. Now we have the distance between these 2 points, and we can use a fit function to create a falloff. So float falloff should be fit this distance from 0 to 2, say. 2 is the maximum radius. And then where the distance is 0, so in the very close proximity to the point, the falloff should be 1. And after the radius of 2, it should be 0, like so. Now we created a nice falloff value. What's left is to derive a scale value from this falloff value. So another float, this time I call it my scale, and another fit function to remap the falloff to a different range. The falloff is in the range 0 to 1, and I want to remap it to 1 to 1.4. So whenever the falloff is 1, the stuff should be scaled to 1.4, and if the falloff is 0, the scale should just stay the same. So now what we can do is we can scale our matrix myTransform by our myScale value. Fingers crossed, let's try this out. Press play and accept, and look at this. Here on this side, and you see that these points are just scaling the cubes up, because wherever a point happens to be, it scales up the boxes. At the moment, this is happening all the time, and thus all the boxes get scaled up because the points are wandering around. So let's put down an enable solver, because we want to execute this scaling thing here only every, let's say, 12 frames. And we can do this by using this enable field here and state $SF for simulation frame modulo 12 should be 0. And the modulus of the simulation frame is 0 every 12 frames. Now this only is executed every 12 frames. You see? Every 12 frames, the stuff that is in the proximity of the point is scaled up. And it's not scaled up by much. That's why it needs a little bit of time until you see really something. But here you see it. Great. Every 12 frames, we get a little bit of scaling where the point happens to be. Time to bring in the other effector points. For this, we want to write a loop and loop over all the incoming points. And to be able to write a loop, we need the number of points that come in. So let's define an integer variable. Let's call it point count and use the function endPoints of input 1, because this is the number of points that come in. And now we want to define the variables tarpos, dist, and falloff before the loop. So let's quickly define them. Vector tarpos, initialize it with 0, 0, 0. Then we'll need float dist is 0 initially, and then float falloff will be 0 initially too. And then we can enter the loop with for integer I is 0, I is smaller than point count, operation is I++, and then brackets, and now we put all this stuff here with the falloff into brackets. Select everything, press tab to bring it over, and get rid of the defining keywords, because we defined the variables already. We are now just using them. And the only thing we want to change now is that we want to exchange this equal sign with plus equals. And that means that this one here, this loop, runs over all the points that come in and adds up all the follows. And one last thing is that we now want to exchange this 0 here for an I, because in every iteration we want to get a different target point. Now press apply, except let's try this out. And yeah, we get multiple points now, every 12 frames. Cool, we are almost finished. There's just one thing missing, and that is all the scaling we do does not affect the simulation whatsoever. And that is because you can scale the intrinsic transform, but Bullet does not scale the collision geometry with the pack primitives. That's a little bit of a problem. We have to tell the Bullet solver that we updated the individual pack primitives. And there is no direct way to update this information. We have to use a trick. And the trick is the ID attribute. Every object, every pack primitive has an ID. And this ID is created whenever the object is created. So if we reset this ID to -1, which is the default value, the Bullet solver thinks that this is a new object and gives it a new ID, and thus recreates the collision geometry. And this will make the scale effect work. So we need another geometry wrangle. And this one is used to update the ID attribute. So create a merge. And before the enable solver, merge this in. And let's call this reset ID. And open the code editor. Unfortunately, the code is very simple. It's just I integer ID is -1. So we are resetting all the IDs whenever this solver chain here is executed. So let's try this. And you see now that simulation is reacting to our scaling, because Bullet rebuilds the collision geometry on the active objects, and everything moves as the cubes scale up. And this is really very, very cool. So thank you very much for listening. As always, I hope you found this tutorial useful, and I hope we see next time. And before I go, let me say a very big thank you to all our patrons on Patreon, especially Mohammed Al-Abdi. Thank you so much for supporting us and making these tutorials possible.